Up until now in this course, we've discussed mostly securing computers and servers. We even talked about mobile devices. But in this unit, we take a look at other types of devices and other types of environments that we may not necessarily always think about when we think about securing computer networks, because a lot of these things don't appear to be computers. So these are alternative environments. This is a relatively short lecture, so we won't spend a whole lot of time on this. So this will be a nice, easy week. But first, let's define what an alternative environment is. So it's non-traditional computer systems and a common information technology environment. So anything that is that we don't think of as a computer but contains a computer really is a computer. And really, this comes from this idea of convergence, the idea that computers are everywhere. Everything contains computers now. Some examples, we're going to talk about SCADA in a few minutes, but these are control systems, so building management systems, things like that. We'll talk about those things. Obviously mobile, which we've talked about before. Mainframes, which are legacy technology, and now, of course, there's newer mainframes, which is very powerful computers. We'll talk about some of that stuff. Game consoles are computers, and we'll talk about some of the concerns with those. And why would you even have those in a corporate or an organizational network? Certainly, there is a place for some of these things. Embedded systems, which we're going to talk about. So all these different things that are, they have computers, they are computers, but we don't typically think of them as computers. Even things like your car. If you think about it, your car has lots of different computers. And we're going to talk about in-vehicle systems in this unit as an example of these embedded systems that we have to manage and we have to worry about as far as IT security goes. And even things that seem benign or seem, like they wouldn't have a computer. For example, refrigerators now have computers. All kinds of devices now contain computers. Your TV can have a computer, these smart TVs and things like that. My DVD player has a computer, your Blu-ray device or something like that, so you can watch movies online and things like that. So all these devices, and we're going to talk about some of these and how we have to worry about those. When we talk about these alternative environments, they're typically static. So what we mean by static is that they don't change. The software is designed and it's put in place in such a way that you're not supposed to really change these systems. It's not like a normal computer where we install software, we make changes to that software over time, we might do updates and hot fixes and things that we talked about in the previous unit. So these alternative environments, for example, with your car, it's not normal for you to make changes to the computer in your car. Now, there may be some people who do make changes to those computers, but most of us, when we buy a car, we don't make changes to those computers. They are basically static. They're not patched. They're not updated. And if they are patched and updated, usually it's a specialist or somebody that knows how to do that does that. Maybe you take it back to the dealer and they fix it, and maybe they put a new version of the firmware or something for the car. So that might be an example of that. There are certainly a lot of highly critical systems that could be alternative environments. So I've probably mentioned this before in this course, but I work mostly in healthcare, in actually in medical imaging. And all of the equipment we use in medical imaging, I would classify as an alternative environment. These are things like CAT scan machines and MRI machines, X-ray machines, mammography, all these things that do X-ray or radiographic imaging and things like that. What's interesting about all these systems is that they are computers. Under the hood, they're essentially computers, but they are actually medical devices. So they're medical devices that happen to contain computers, but they have to be very static. They have to be very controlled environments. You can't be making a lot of changes to those systems. If you design a CAT scan machine, and remember, a CAT scan machine can have dangerous amounts of radiation. And if that gets messed up, then you can cause significant harm to patients. So it has to be very carefully controlled. And this presents challenges to us in IT security because, number one, you don't want a hacker being able to get control of those systems and being able to modify or be able to do malicious things with those systems because it could affect people's lives. Normally we're just talking about some data, maybe even data that's not that important, maybe that might cost us money. But when things start to cost the health and welfare of patients, then it's a whole different game. And we want to make sure that those things are secure. So we'll talk about different ways to do that. But the other thing is we can't always patch those systems. So, for example, an X-ray in my world, we can't just take an X-ray machine, even though it might be running Windows or some embedded version of Windows under the hood. We can't just put hot fixes and patches on that. So if there's some zero-day vulnerability that might affect that machine, we can't go in and just update it to fix that vulnerability because we don't know how it's going to affect those highly specialized systems that if we screw those systems up could have disastrous consequences. So We can't always do those things. Maybe we can rely on the vendor to do that, and the vendor may tell you that they're not able to do that for a variety of reasons. It might break something. The FDA certainly has opinions on whether or not we can do things like that, and the FDA has usually said that we should not make those types of changes to these embedded systems in medical imaging. So again, it presents kind of a challenge. How do we deal with that stuff? I can't, in a hospital environment, you can't say, well, I'm just going to go ahead and take that X-ray machine off the network because it's not patched, or because I can't join it to my domain, or for whatever reason, whatever IT security policy that it can't comply with. We can't just remove it from the network. We have to make sure that we can work with that stuff. And we have some kind of roadmap to deal with those challenges. So again, it's typically static, unlike our other IT infrastructure. So we have to be able to deal with those types of things. As I said before, it's constrained to a limited, defined set of functionality. So unlike other computer systems and servers, which have all this different functionality and we can do lots of different things with them, embedded systems are typically designed with one purpose in mind, or a very focused set of things in mind that it does. It may have software that's capable of lots of different functionality. It may be a Linux machine under the hood, or it may be a Windows machine under the hood. But a lot of those things, a lot of that functionality has been stripped away, and it has one focused set of functionality. So that's typically what defines these alternative environments. So the first thing we talk about, the first alternative environment that we discuss in this unit is supervisory control and data acquisition. So what is that? Basically, it's control of automated systems. So some examples would be things like manufacturing, or traffic lights is a good example. Traffic lights are, when you think about it, somewhat complex how traffic lights work, but they're controlled by computers, and those computers are very simple. They have a very focused purpose, but they have to work right. Think about what would happen if traffic lights started malfunctioning. You could have disastrous consequences, cars hitting each other at 90 miles an hour. I mean, it could be very, very dangerous. But think about it. When's the last time you've heard of a traffic light malfunctioning? It doesn't happen very often. And when they do malfunction, it's usually on the side of caution, where the light might blink red or something like that to let people know that they should use caution when they approach the traffic light. But all of that stuff is controlled by what we call SCADA systems. Oil refineries and things like that. They use, they have these big control rooms that you might see on TV, and likewise, energy sector and and water and sewer. All of these systems have these, these control rooms that control all of this industrial equipment. And if that stuff doesn't work right, it can cost significant amount of money. It could cause a lot of problems. Obviously, we all like our toilets to flush and the water to come out of our spigots. So it's important that those things work. And a lot of this is controlled through SCADA, through these types of systems. One example is a nuclear power plant. It's computers that control those nuclear power plants. And of course, it's absolutely critical that those systems remain secure. And really, the only way to make sure that those systems remain secure with 100% certainty is to air gap them, which we're going to talk about in a few minutes what that means and what we're referring to with that. Building automation is another example of SCADA systems. So things that control temperature, and all the different things that happen inside of a building, so that those are basically are typically SCADA systems. You might also hear these referred to as distributed control systems or industrial control systems. So the abbreviations are DCS and ICS. So same as SCADA. So previously, in the old days, all of these systems, because people knew how important and how critical they were. I used the example of a nuclear power plant just a few minutes ago, and one really powerful way to keep hackers out of that type of system is to air gap them. Air gap meaning that they have no connection to a network. They're completely disconnected. So they may be networked internally, so they may have networking that talks to different components, but there is no connection to the public internet. And even on a local area network, there is no connection to the local area network. So what we mean by air gapped is not that we electrically isolate these systems, not that we put a firewall in to separate the nuclear power plant's control systems from the rest of the network. That firewall could conceivably, as long as there's an electrical connection that can be made to the public internet, there's always that possibility that's going to get attacked, and it's going to, somebody can break in, no matter how good those firewalls are. So if we want to make absolutely 100% sure, we're going to have to air gap, meaning that that it's not physically connected, not through wireless, not through copper, nothing. It doesn't exist. One of the really good examples, and your book talks about this. There was a virus not long ago called Stuxnet, which is a great example of how or why air gapping is pretty much the only way you can completely protect a network from attack when it's critical systems. In this case, Iran was trying to use centrifuges to separate uranium to produce. It might have been plutonium, but they were trying to produce nuclear fuel to build presumably nuclear weapons, although they claimed it was for nuclear power plants. So they wanted to destroy those machines. So the NSA discovered what types of machines they were using, what type of centrifuges they were using. They figured out the manufacturer, and through various sources, they were able to find out exactly what model numbers the Iranians were using. They developed a worm that, when that worm found itself on those specific systems, it would destroy the machines. And how did the worms find those machines? Because they were somehow connected to a network. So those worms just eventually made their way into that protected network. It could have been somebody bringing in a laptop, a USB drive, who knows? But it breached that network, was able to destroy those centrifuges. So it was definitely a win for U.S. and Israeli intelligence to destroy those machines. However, it also exposed the vulnerability in these types of systems, in these alternative environments. Now, that's an extreme example, being a centrifuge for creating nuclear fuel, but a lot of manufacturing equipment uses these embedded systems that I've talked about. So they would have to be protected. And there's a good chance that some of you may find yourself working in an environment that contains some of those types of systems. If you work at a factory, or if you work in any kind of high-tech industry, there might be these types of equipment that has to be protected from being attacked. So embedded systems are basically computers that are included as an integral part of a larger system. That's what they're talking about with embedded. So here we're talking about things like printers, smart TVs, thermostats, all these devices that have a small computer in them in order to provide some kind of functionality that's easy to do with a computer. So, for example, printers will typically have a computer, a computer that has this very specific purpose, but they're still computers. So if you go out and buy a multifunction printer that has wireless networking, so you don't have to plug it into your computer, physically plug it into your computer to print, and chances are it has an embedded system, an embedded computer. In most cases, these are lightweight operating systems. So a lot of times there's some distribution of Linux, or a very watered down version of Linux. Smart TVs, a lot of those run some distribution of Linux on the back end. Thermostats. Nest is an interesting company that makes a thermostat that it's a smart thermostat. It connects to the internet. You can control it over the internet or from your smartphone. It has machine learning, so it can sort of figure out when you're occupying the house and how to adjust the temperature for the best utilization of electricity and things like that. They're really cool devices, but they include computers. And again, because they have these computers and they connect to our IT infrastructure, we have to be aware of them and know that we have to protect them from being attacked. So they're designed for a single purpose, but since they are computers, they have capabilities that are beyond their intended purposes. So, for example, that thermostat, while its intended purpose is just to be a thermostat, it does have a Linux distribution baked into it, that little Nest. And I'd be willing to bet that there are people who have hacked those Nests to do all kinds of things that they weren't designed to do. So, for example, you might be able to turn your thermostat into a web server, or maybe turn your thermostat into an FTP server, or who knows. So all kinds of things. Anything that you could do with that operating system, those core components exist. They're there. If the storage is available and the resources are available, or if you can find some way to make it work, there are always ways to sort of hack those things. And sometimes that stuff can be kind of fun, but again, it might turn that device into something that it wasn't intended to be. So also consider more advanced systems and the possibilities to take advantage of them. So, for example, climate control systems in a building, you might be able to access those computers that are embedded in those devices to change the temperature or wreak some kind of havoc on a building, or take control of HVAC. Even elevators have these embedded systems. So newer elevators have, rather than designing custom electronics to control the elevator, it's just easier to embed a small computer that can do all that. But again, that computer can be hacked, and then somebody can do something malicious with that elevator. Maybe make people stuck in the elevator, or have it randomly go to the wrong floor, or who knows. All kinds of things. You can mess with different alarm systems. So fire alarms and intrusion alarms, all of these things could have embedded computer systems in them. So again, it's important to know that these things exist and that we have to protect against those. I keep talking about protecting these systems from attack. We're going to talk about that at the end of the presentation. I'll talk about some methods at the very end that we can use to protect these systems. So we've already talked extensively about phones and mobile devices. We've covered that in previous units, actually several times. And we've talked about how that would include things like cell phones, tablets. In addition, with the alternative environments, we could also be talking about specialized handheld devices. These could be little scanners or receipt printers or card swipe things that maybe salespeople use on the floor. Think of your UPS guy that delivers you a package. Usually you sign a little tablet, and that's not a typical tablet that you or I could go buy at a store. It's a specialized tablet that has specialized functionality. That is an alternative environment, and it probably has firmware, and for sure it has software. It's probably running some version of Linux or something like that. So the environment is not as static as other alternative environments, usually these phones and mobile devices. So most of the things I've talked about so far, they might have a very focused or a very specialized distribution of Linux, or it might be very customized, and it's very static. We don't really change it because it has that one job that it's supposed to do, and we really don't make any changes to that. But our phones and mobile devices, I probably don't have to tell you guys that they can do lots of things. My phone is really almost as powerful as the computer that I have on my desk. I can do all the same things. I can check my email, I can instant message, I can use Facebook, I can browse the internet. So we use it for lots of things. So they're definitely a lot more dynamic. So we certainly have things like patches and hot fixes, as we talked about in the previous unit. Those are much more common in mobile devices. And of course, updating firmware. Periodically our smartphones and things like that are updating themselves. And, it might reboot overnight. And you wake up the next morning and all of a sudden you have a new version of the firmware for your Android phone or your iOS device. So in our book talks about Android and iOS, it talks about some of the specific concerns that we might have with Android and iOS, but the big one they talk about is jailbreaking those devices. So your book sort of talks ominously about jailbreaking and how dangerous jailbreaking could be. I take the other view of jailbreaking that, what they talk about in the book is that when you jailbreak a device, you have root access to that device, you have escalated privilege to that device. Now your book views that as not such a good thing. However, myself, I view that as a good thing. I think if you asked anybody in IT, would you want to have equipment or IT infrastructure for which you don't have privileged access to? That would make most of us nervous to have some device or some computer in our network that we just simply don't have administrative access. Only our vendor has access to it. I don't think I'd feel too good about that. So I would prefer to have that privileged access or have the ability to get that privileged access and be able to do whatever I want with that device. After all, we own that device. But that ownership of those devices is actually kind of in question. And it's been sort of a legal question for a while now that hasn't really been satisfied. But again, your book talks about jailbreaking as this ominous thing that, could wreak havoc on your network if you have jailbroken devices. But I prefer to think of jailbreaking as freeing a device and being able to understand it better. And, it's a lot easier to secure things that we fully understand. So I don't really view jailbreaking as a bad thing. So I divert a little bit from the book in that area. Your book talks about mainframes, which are large, high-performance systems. Most of these are legacy systems, so mainframes are usually thought of as legacy systems, although your book, I think, inaccurately talks about how mainframes are, host virtual machines and things like that, but I would not consider those mainframes. So if you've got a large computer hosting virtual machines, you probably have some kind of VMware cluster or something like that. And I would not classify that as a mainframe. It might be a powerful computer, but it doesn't really fit the definition of a mainframe. So mainframes are typically legacy systems. They can be quite powerful. They're usually very focused on transaction processing and things like that. You usually find mainframes running large financial institutions, airlines, logistics types of things. Anything you might see, SAP, might have a mainframe in their organization. So if you work for or with any of these organizations that might use mainframes, you would also have to secure these as an alternative environment. And as we discussed with other alternative environments, again, we don't always have control to patch these things. They have very specialized, we have to really be kind of hands off with this equipment because, it is very critical to the organization typically. Think about a bank that runs a mainframe. If that mainframe has problems or it crashes, the bank is basically shut down. So these are very critical systems, and chances are they're not like a typical computer. You're not going to go, you can't use that system to surf the internet, for example. They're not even going to have a web browser included typically. But all of the components will probably be there, though, unless they're a very legacy system. And a lot of times they're wrapped with middleware. So we're going to talk about the concept of wrapping later on, but they might be wrapped with middleware that sort of protects those systems. And sometimes the middleware is required for other reasons, but we'll talk about that later on. Game consoles are usually designed for entertainment. Why would you have them in a business? So a couple different reasons. One I think is you can use game consoles. You can repurpose them for clusters for supercomputers. So the United States Air Force actually built one of the most powerful supercomputers at the time, one of the most powerful supercomputers in the world using, I believe it was PlayStation 4s. They clustered maybe a couple hundred of them together and made a huge supercomputer out of them. And the reason they do that is because a PlayStation 4 had some pretty powerful hardware for the price. You can buy a PlayStation for, I think it was, $400, but it had probably almost $1,200 in computer components in it. So if you went to Best Buy and bought a computer equivalent to a PlayStation in specifications, you would have to drop about $1,200, maybe even more. Or you could buy a PlayStation and you could, I use the term jailbreak, but you could repurpose that as a computer. And in this case, they clustered them and made a huge supercomputer out of it. So some organizations have done those types of things with PlayStations. It could just be a game console. There could be some reason that it exists on the network as literally a game console, maybe just for people to blow off some steam or what have you, or it could have been repurposed. So who knows? But if a game console is in an environment, again, we have to know that those are alternative environments in the sense that they are specialized hardware with specialized operating systems that we really don't have a lot of control over. We really can't do a lot of patching and things like that. But again, it does have a more focused use, which is in this case for playing games. But it's a little less constrained than some of the other things that we talked about. So they might include the ability to surf the internet. They might have the ability to use other applications. So there's certainly other things that you could conceivably do with these game consoles out of the box without having to repurpose them or jailbreak them or whatever you want to call it or root them. So that does increase the attack surface a little bit over some of the other things that we talked about. But I would say that they're probably a little bit more secure than some of the other things that we did talk about. The last environment that we talk about that might be alternative is in-vehicle computer systems. Certainly corporations and companies and organizations have company cars or people are using cars. So in-vehicle computer systems are divided into two categories. You have vehicle control and then entertainment. And prior to the last several years, most vehicle embedded systems or in-vehicle computing systems were mostly for vehicle control. So they were, all the computers that control our car that we don't really have a user interface to. They just kind of do their job under the hood, literally under the hood. But we don't really think about those things. We push the brake and there's a computer that figures out if the tires are locked or not. And if they are, it might take control of the braking system and, do all that anti-lock stuff that you see in the commercials. And then the other category is entertainment, which is now very common. So most newer cars have these entertainment systems that are embedded in the car. They have an operating system. They have a user interface. They act a lot like computers. They have GPS built in. You can use it to connect to your phone for Bluetooth and things like that. So these systems, one thing that your book talks about is the emergence of vehicle to vehicle and vehicle to roadway communications. The idea that at some point cars will be able to talk to each other. Cars will be able to talk to the roadway. So maybe the roadway will tell them about traffic or about hazards or other vehicles on the road and things like that, almost like we do with airplanes, right? Eventually, there may come a day when cars are going to drive themselves. Google's been trying to build a self-driving car for a while, although I think psychologically, even though we might be there technologically, psychologically, I think most people are not there, are not ready to relinquish that kind of control to their vehicles. But all of those things present new security risks that we have to be aware of. Those entertainment systems can also expose data or can be used inappropriately. One example I think I've talked about in previous lectures is whenever I rent a car, in many cases, I'll find somebody's contacts in the radio. They'll sync their phone with the, and this is pretty common with the Microsoft based systems, and Ford, I've seen this a lot, where they'll sync their device with the car, it'll pull all of their contact information into that computer, but it never gets deleted. So by the time you rent that car, there could be 4 or 5 other people's contacts all in that computer, and you might even find their text messages and their calendar and all kinds of stuff. So it would certainly be a good idea to let employees know that when they do use a vehicle like that might be used by other people, to be cognizant of that and make sure that the data doesn't get siphoned off into that car. Here's a good example for you. Let's say somebody rents a car and they're an executive for a large company, and they've got maybe text messages talking about some kind of big merger or some big event that's going to happen within that company that would be interesting for other investors to know about. So let's say later on they return that rental car, and somebody from an investment company gets in the car, and they are able to find those text messages and say, "Oh, look at that! The XYZ Corporation is going to be merging with the A Corporation, so I should go buy some stock in the A Corporation," or maybe use that for some corporate espionage or something like that. So lots of things you have to think about with all these interconnected embedded systems. Again, a lot of these embedded systems in cars are not really there yet as far as the vehicle to vehicle and vehicle to roadway that your book talks about. But a lot of the other things I talked about is certainly plausible. So there are various methods for protecting these systems. Probably the most common is network segmentation. The idea that basically we take all of those systems that are alternative devices and we segment those from the rest of the network. We put them on their own network where they have no connection to the other devices. So we do this pretty frequently in medical imaging. We'll take all of these medical imaging devices like the CAT scan machine, the MRI, and the X-ray and the mammography, and all these systems that have these embedded systems and whatnot, and we'll keep them segregated from the rest of the network so they're not connected. They have no way to route traffic to or from the real hospital's network. But in order to get the data from those machines to the rest of the hospital, we'll send it through some other machine that we can. So here's a common scenario. It's almost impossible to install antivirus on a CAT scan machine, even though it may run Windows, or an MRI machine that may be running Windows. We may not be able to inoculate against the heartbleed bug if we're running Linux, for example, because it's these embedded systems that we can't apply these patches to. There's just has to be too much control. So instead, we have a server that all of those machines might connect to, that they route all of their traffic to, and that server might straddle both networks. So they might straddle the real hospital network, and they might also straddle the radiology side with these specialized systems. And that system, because it's not a device and it might be just a regular Windows server, that can be inoculated against all of those issues that we've talked about already. So we can have our security policy on that machine, where we can have our antivirus, we can have our malware detection, our intrusion detection. All those things we talked about could apply to that machine, and it connects to both sides. So if a virus, for example, or a worm is making its way around the network, hopefully that machine is going to stop it before it gets into those other systems downstream. And of course, it's not foolproof. It could still happen. And the only way to really keep that from happening, as we talked about before, is to air gap it. In other words, make sure that there's zero connection. But that's not always feasible, because all of that information on those machines is useful for doctors, and they'd like to see that stuff. So we do need to have a way to get that to the rest of the network. So the advantages of doing that overcome some of the risks that we have with those systems getting shut down by IT security incidents. We talk about layered security in IT security in general. We've talked about that before in this course, and all of those concepts can also apply to these embedded systems in all of these alternative environments. Application firewalls can be used, which I just talked about, right? So what I just talked about is the concept of an application firewall. We had that machine that straddled these two different networks. So that's certainly another example. We can use manual updates to update those systems. So again, going back to my hospital example, because that's what I'm familiar with for the most part, we don't allow automatic updates on those machines. Anytime those machines need to be updated with new firmware or with new hot fixes or patches or anything along those lines, it's done by a technologist, or it's done by a technician that is familiar with the equipment and does those manually. We don't allow those things to happen in an automated way. We might have firmware version control. We want to make sure, what we're saying here is we want to make sure that anybody can't walk up to a machine and update the firmware to take ownership of that machine. Remember, if you have physical access to a machine and you can do a firmware update, you can put anything you want on there, and then you could take over the machine. and even if, and especially if it's for malicious purposes. So that's another option. I talked about this term wrappers before. We'll go back to the mainframe example I talked about before. Let's take a bank, for example. If you have a bank that's using a mainframe for its transaction processing system and basically to manage all of these bank accounts, that's probably a good example of what mainframes might still be used for. They're legacy systems, but what you could do, so one thing is most of us, excuse me, most of us like to do online banking, which is essentially using the internet to do our banking. But those mainframe systems, we certainly don't want those connected to the internet, at least not directly. We want it to somehow be segmented. So you might use a wrapper or what I would call middleware that sort of wraps around that mainframe, and all of these third-party systems that might interact with that mainframe system go through that middleware. They're through that wrapper. So that wrapper is doing all the modern IT security functionality that we've been talking about. It might be protected from things like SQL injection. It might be protecting from all of these various types of attacks that we talked about, and it's on servers that we can protect, and they're the only things that are allowed to talk to that mainframe that's behind that wrapper. So that's an example for you of how you might use wrappers. And we talked about wrappers before. So we talked about wrappers in the previous unit when we discussed TCP wrappers, and it's the same concept as we talked about before with TCP wrappers. So we talked about a few things with alternative environments. Alternative environments can certainly be a challenge, but most important thing is to understand what you have that is an alternative environment, and know that we need to protect those things. And as I said, we can use some of those methods we talked about. Network segmentation is probably the safest route for a lot of these things. But the most important thing is to be aware of them and know that we have to protect against those. So this week was a rather short lecture, give you a little break from the grueling work that we've been doing in the other units. If you have any questions, please let me know, and thanks for watching.